Good afternoon again to the live interactive session for the NPTEL course Advanced Transition Metal Organometallic Chemistry. So, as we have already come to the almost end of this course, today is the week 11. So, after this week, only 1 week is remaining, that is the week 12. So, for this course, starting of the week 1 to this week 11, we have seen different kinds of organometallic ligands at starting with different number of carbons, starting from carbon number 3, and we have ended our discussion with carbon number 8, and then we also discussed some heterocycles, that is containing some heteroatom like oxygen, nitrogen, sulfur, etc. In this course, we are discussing the most important part, that is the applicable of this organometallic compound in the field of catalysis. Mainly we are discussing that types of catalysis which are applicable in broad range, mainly in industrial processes. We have seen Suzuki coupling reaction, palladium catalyzed Suzuki coupling reaction, Heck coupling reaction, Stille coupling reaction, as well as some carbon heteroatom bond formation reaction like hydroboration, hydrosilylation, hydroamination, etc. But now at the end of this course, we are seeing some catalytic reactions which are mainly the oxidation reduction type of reaction catalyzed by different metal, not only the palladium. So with that, first we have started olefin oxidation reaction. Then in this week we are discussed mainly the oxidation reduction reaction of carbon monoxide, because all we know that carbon monoxide is a very toxic gas to the society and to the environment, and this carbon monoxide is mainly released by the industry in a huge amount in every year. So converting this carbon monoxide to other value added chemicals is very important to decrease the toxicity effect of these gas released by the majorly the industries which uses hydrocarbon as a fuel. So we can convert their release of this CO gas to the value added chemicals through different catalysis, which will be helpful for your society, for our society, as well as for our environment, for better living. For that we have discussed in this series week 11 with the oxidation and the reduction of CO gas. First, this CO gas is oxidation to give the CO2. Now CO2 is again toxic, but we can convert CO2 is a part of the synthesis gas, that is CO2 plus H2. So now if we convert the one toxic gas like CO to CO2, and by combining with hydrogen, that is CO2 plus H2 as a synthesis gas, this gas now can be used for several industries to convert to other valuable chemicals. So and then the reduction of the CO gas to different hydrocarbon. So first one is the oxidation of CO, which we call the Weber process, and then the reduction of CO, that is the Fischer-Tropsch synthesis. So these two processes of these in this series is very much important. Why important? Mainly that we are using the wastage, that is of the industry, that is which is come out as their waste as our starting material or as our reactant, to convert this waste to a value added chemical, and we are saving the environment. And so first we have seen that the oxidation of the CO gas, then the reduction of CO gas, then we have seen some carbonylation reaction, and all, that is the conversion of methanol to acetaldehyde, and then to, we have seen that the synthesis of acetic acid, and then methanol to, with the help of acetic acid we have synthesized the industrially important acetic anhydride. So all these things are very important and undergo happen by the organometallic catalysis. So at the end of this course we are seeing the importance of the organometallic compound in the field of catalysis. So as I am discussing in few last lectures of this discussion session, that going through the slides is very boring and it is not interesting at all. So our main approach in this session is to know how the questions in the assignment, the question in the assignments, that is in the portal, as well as the question which will come in the final exam, how the question can be approached, and with the help of knowledge and trick and understanding of this course content, we can find out the correct answer from the given choices. So without wasting, as I will wait for another 2 minutes or 3 minutes to watch or to see if any participant came. If not, then I will start this session from my side to discussing the questions which is closely related to the assignment problem, and closely related to the course content, for better understanding this weak content and to easily solving the assignment problem. So I will wait for 2 minutes, then I will start discussing the students to today's discussion, that is the weak content through the problem solving session. So I will wait for another 2 minutes, then I will start discussing the question of this week. Okay, now I will start discussing the questions which is closely related to the assignment problems and of this week, and then and I will start and then I will show how to solve these questions and what is the theory or understanding behind this topic. So as I am sharing the screen, so I will start turning off this video and I will turn it on again when I need to talk. Okay, welcome again for this interactive session for the course Advanced Transition Metal Organometallic Chemistry. In this course, in this session we are mainly discussing some questions for which is related to the portal assignment problems, and we are discussing the question in terms of this week's content. So this week content to for better understanding that point and to show the approach of this question. So without wasting any time, let's start with the today's first question. Today's first question is the water gas ship reaction involves the conversion of. So as to answer this question, we need to discuss what is water gas ship reaction and what is the importance of this reaction. So as I have already mentioned that water gas shift reaction is basically the reduction of and the oxidation water gas shift reaction and the Fischer-Tropsch reaction. These two reactions are basically the oxidation reduction reaction of CO. Water gas shift reaction is the oxidation reaction of CO, and Fischer-Tropsch reaction is the reduction of CO. So with this you get an idea so what happened to the CO. So as if we go so that is and the combustion, and we are getting the CO mainly from the industry where we using the hydrocarbons. Hydrocarbons are or crude oil, that is the crude oil, which is generally a source of energy in different industry. So to convert this toxic CO gas to halogenated chemical is important. So now the water gas ship reaction described as here H2O plus CO catalytic by FeCO Fe copper couple, that is the heterogeneous catalyst and it is converting to H2 plus CO2. So this is the simple expression for the water gas ship reaction, where delta H is minus 42 kilojoule per mole. So, this signifies the equilibrium lies in the exploration of reduction power of, so that is the reduction power of CO to produce the high H2 from water under mild condition. Here temperature is greater than 200 degree centigrade. The removal of CO from the gas mixture from the Haber-Bosch process, H2 enrichment the synthesis gas for Fischer-Tropsch synthesis. So this combination H2 plus CO is called the synthesis gas. So the as our CO2 is converting to a mixture of gases, which is important for other chemical reaction. Now we need to know the mechanism of this cycle. So Waker process is the conversion of CO to CO2, that is here CO is in plus 1, here it is plus 2, that is water gas shift reaction. This is not Waker process, this is the water gas shift reaction. So water gas shift reaction is converting CO to CO2. So water gas shift reaction is CO to water gas shift reaction is CO to CO2, that is the oxidation of CO. So now, sorry for that, this is not a Waker process. Waker process we have already discussed in last lectures and last discussion series. So this is a water gas shift reaction. Very sorry for that. So this is a water gas shift reaction where we are converting the CO to CO2 as it is the oxidation of CO. So now our answer will be option A, that is the conversion of CO to CO2. With this, go on to the next question. The reduction of CO by hydrogen to the hydrocarbon is performed by. So as I already said that water gas shift reaction and the Fischer-Tropsch synthesis are counteractive. That is, so the water gas shift reaction is the oxidation of CO, and Fischer, this is the reduction of CO by hydrogen to hydrocarbon. This is the it is the reduction of CO is reduction of CO is reduction of CO is Fischer-Tropsch synthesis. So the reduction of CO is the Fischer-Tropsch synthesis. So we know these two reactions are counteractive. That is, the one is to opposite to other. So water gas shift reaction is the oxidation of CO. So it is CO convert to CO2, and it is the reduction of CO convert to hydrocarbon. So this is the so now we get how which process is called which. Our third question is, the water gas shift reaction is catalyzed by. So as we seen that our water gas shift reaction is in this, see that our water gas shift reaction is catalyzed by catalytic iron copper couple in as a acting as a heterogeneous catalyst. So the reduction happens on the surface of the catalyst. This is called the water gas shift reaction. So water gas shift reaction is catalyzed by, so water gas shift reaction is catalyzed by our iron copper couple. So here option A will be right answer. Now going to the next question, the composition of synthesis gas is. So as I have seen that the oxidation of CO generate the CO2 gas, that is oxidation of CO convert CO2. So the synthesis gas is our CO plus H2O. So this is our so our synthesis gas is or syn gas is CO plus H2. Here our composition for the synthesis gas is CO plus H2. Going to the next question, that is the question number 5. That is the following reaction the following reaction is an example of. So, so here we have seen that this kind of reaction when we are dealing with the carbonylation reaction. So here we can clear. So our options is the oxidative addition reaction, reductive elimination reaction, a migratory insertion reaction, or a transmetallation reaction. So So in this reaction we are having that this CO group is undergo the insertion of this metal hydride bond to give right C double bond OH metal. So this is a kind of migratory insertion reaction. So this reaction we have discussed in more detail when we will discuss the Monsanto acetic acid synthesis reaction from methanol. So that is the Monsanto acetic acid synthesis reaction from methanol. We will discuss it in more detail. So this reaction is basically, you can see that this CO group is inserted into the metal hydrogen bond. So this reaction is called a migratory insertion reaction. So for this question, it is a very interesting question that if we go by these options, that is an oxidative addition, reductive addition, migratory insertion, and transmetallation. So we have discussed all these terms, and all this term is for at least these two terms, and this term is known. We have discussed these three terms in most of the reaction. At least the oxidative addition and reductive elimination term we came across for all types of reaction except for the heterogeneous catalyst reaction. This oxidative addition step and the reductive elimination step. So but here the oxidation step of this metal is not changing any time. Also no product elimination we have seen. So the only option, and also the transmetallation, that is the no other metal involved in this reaction to perform this transmetallation. Transmetallation is happen that time when we are having two metals in the system. So here only one metal is present in our system. So by going by the option, we can easily go to the answer for this question, that is migratory insertion reaction. So this technique or this trick I have discussed in earlier also. So in all the time it is not possible to get the correct answer, and it is not possible to know everything for this. But if you go through the options and think whatever the knowledge we have gained till now, we can find out the correct answer with the maximum probability. Sometimes we are going by the option elimination trick, which I also discussed in previous or uh, 2-3 session back. That is also an important and interesting technique to get the correct answer of a question. So here we got our correct answer for the question number 5, that is the following reaction is an example of. migratory insertion reaction. Going to the next question, that is that this question is very important. As why? Because here the question is the compounds 1 and 2 of the following reaction sequence respectively are. So in these types of sequence or in these types of thing, we have to know the all the two product for this reaction sequence. We need to know the product 1 and also product 2, so that only then we will get the correct answer. So here we are discuss this thing, that is the CO plus H2O is copper catalyst, that is it is going to give our methanol, that is the reduction in through the Fischer-Tropsch synthesis way. So I have already seen that the oxidation of the CO to CO2 is called the iron catalyst to give the CO2 as a water gas shift reaction, and then the reduction of this CO is called the Fischer-Tropsch synthesis. So through the Fischer-Tropsch synthesis we are generating hydrocarbons. So here through that reduction step we will have our methanol as a product for the one. So as the methanol is both the option C and option D, both places are present, so we can easily eliminate the option A and option B. Here the same thing applied. So if we know the one of the answer, either 1 or 2, we can easily eliminate the two options. That is, our probability to getting the correct answer out of these 4 increased to 50%. So now we have seen that in presence of CO our catalyst is rhodium, in presence of iodide 180 degrees centigrade rhodium CO2 I2, that is our catalyst. So in this catalyst we are getting the acetic acid as a product, so that is the Monsanto acetic acid synthesis. Here the role of I2 is to converting CH3OH methanol HI as an acid to convert it to CH3I. So methyl iodide, here the iodide is a very good leaving group as well as a good nucleophile. So we are using HI plus water in catalytic. Also it help our product that elimination, that is through the reductive elimination step. So our answer for this question will be option number D, that is the synthesis of acetic acid and from the methanol. So with our rhodium as a catalyst at 180 degree centigrade and 30 bar pressure. With this, the mechanism of this reaction we will discuss in later on. Then the catalyst used in the Tennis Espen Halcon SD process. So this process, which catalyst we are using? So this process is mainly applicable for the synthesis of acetic anhydride from our acetic acid and methanol. So for this question, our catalyst here is also our catalyst is the rhodium catalyst, that is the CO2. CO2 RHI2. So this catalyst is the synthesis of our acetic anhydride from acetic acid. The catalytic reaction for this Tennessee-Eastman-Halcon SD process, which is used in 1983 in the carbonylation of methyl acetate. So here our reaction is CO plus 2H2 is converting this to CH3OH, that is the methanol. Now this methanol in presence of acetic acid is converting to methyl acetate, that is an ester. That is called the methyl acetate, that is an ester. Now in presence of CO and our catalyst, it is giving to acetic anhydride, acetic anhydride. So this acetic acid is coming from the industry. This acetic acid is coming from the industry and as a byproduct, and this byproduct is used to convert it to a value added product, that is the acetic anhydride. The direct formation under the homogeneous catalysis is important. So in Dennis Eastman Halcon SD process is catalyst is the cis CO2 RH to generate the acetic anhydride in presence of acetic acid to convert the carbonylation of methyl acid through the methyl acetate to the ester. So with this I completed the 7th question of today's series. Now we need to go the 8 question number 8 for this discussion. Probably this is the last question for today's discussion. After that we will discuss some important theory from the for this week which is not to discuss. So here the question is for methyl carbonylation, that is which are seeing in the last question, that is the acetic acid synthesis and acetic anhydride synthesis, that is the carbonylation reaction of methanol. Here we have got our catalytic cycle. We will explain the catalytic cycle and first we will get the answer, then we will explain each step of this catalytic cycle. So now the question is for methanol carbonylation catalytic cycle is already given. The step 2 is known as, so we are asking for this step, that is the step number 2. So here it is oxidative addition, reductive elimination, rearrangement or insertion. So which will be our correct answer? So now to get the correct answer, as we think that in last few question we have some, we can get our option by simple knowledge of catalytic cycle. So here our option is oxidative addition, that means the oxidation step of the metal ion should be changed. So now as this here to here there is no change of oxidation state of the metal, so there it is not an oxidative addition reaction. So this is not an oxidative addition. Also the reductive addition, same thing, that is the reduction, also the product elimination. So here nothing is eliminated and also the oxidation state of the metal is not changing. So it is also not a reductive elimination. Is this a rearrangement? No. It can be called rearrangement in terms of cis or trans, but here we can see that this CO group is again inserted in between this CH3 to give COCH3. So this is not a rearrangement. Not a rearrangement is terms of cis trans. So it is also not a rearrangement. So our correct answer will be insertion reaction. So with this I completed the most important topic through the question solving session of this today's lecture series. Now I want to discuss some important point of this week through different content. Now first we need to know or we need to explain this mechanism of the catalytic cycle or this reaction. Here we need to know the mechanism for this reaction. first mechanism I will start with this one, that is the mechanism. We are going to discuss the mechanism of the reaction. That is, our mechanism is the carbonylation of alcohol. Carbonylation of alcohol. For that, our reaction is, which I already discussed, CO plus 2H2 with copper catalyst produced methanol. Now this methanol is converting in presence of CO and rhodium catalyst in presence of iodine and 180 degree centigrade using 30 bar pressure is converting to CH3COOH. Is called the Monsanto Now this selectivity is greater than 99% and the capacity is 10 to the power 6 ton per annum. That is, this process we are producing the acetic acid, which is a very industrially important chemical in different field of industry. We are having the acetic acid. Now it is produced 10 to the power 6 ton per annum. So the catalytic process follow the mechanism which I show in this slide. So now need to explain this catalytic cycle through the here the role of iodide ion is very important. The role of iodide ion, the role of this iodide ion is very important. The role of I minus is very important. So it convert methanol into the stronger electrophile methyl iodide. So this is very important, the role of iodide in this reaction. Now we need to see the catalytic cycle for this Monsanto acetic acid synthesis reaction. So what will happen? So first we have our methanol, that is CH3OH. Now this methanol in presence of HI, it is converting to methyl iodide and HI become to H2O. Then and we have our catalyst, that is the rhodium CO I minus, that is the cis orientation. Then this will undergo the catalysis in this cycle, that is the step 1. Here this step 1, as I already said in last question, is the oxidative addition step. So oxidative addition with this give the rhodium CO. So this is the oxidative addition step. So to give the rhodium is complex. Now this intermediate will transform to the another step, that is the step 2, which was our next question, that is the insertion. This step is very much important, and this step is called also the rate determining step, and this is the slowest step of this reaction. So this will give rhodium I CO CH3 and CO. Minus. Now this step will undergo the step 3. The step 3 is again the carbonization step of this unsaturated, coordinatively unsaturated complex, which will give rhodium I CO COCH3 minus I CO. Then this step will undergo the reductive elimination step to give CH3 this. Now this is not our desired product. Now in presence of water, this step, in presence of water, this generate the hydrolysis to undergo the acetic acid. So water is this what, so here HI and water also act in a catalytic manner. So here another very important question, when we understand this mechanism, another question came to our mind. So what will happen? So if we do, so our one question came our mind, that question 9, what will happen if we perform the reaction? Reaction means here the same reaction which we are discussing, that is the carbonylation of methanol to give the acetic acid. Reaction in D2O in presence of H2O. So here, that is, so here we have seen that CHOH is converting at in presence of HI and H2O to methyl iodide. Now this H2O is held to hydrolysis of this molecule, that is the reductive eliminated product. Now if in presence of, if we use D2O So in presence of D2O, this thing also hydrolysis to give. So we get, if we use the D2O in presence of H2O, we will simply get the deuterated. But here you need to think that this H, this in this mechanism, this Hi is converting to H2O with the help of this OH. So there is a possibility to obtain this product, but as your methanol, that is this in hydrolysis in presence of this to get this, but in our catalytic cycle we have seen that this methanol OH group in presence of Hi is converting in presence of Hi converting to H2O, and I minus is attacked by this to give the methyl iodide. But here this product will obtain, but the majority of this product will be COOH if we start with the CH3OH. So the obtaining of this product is lesser amount, because the hydrolysis product is only obtained if we use the Hi as an acid. So this is interesting and thing to note. Also, in catalytic cycle we are having the different step, that is the insertion step. Here the insertion of this carbonyl group happen to the methyl group, methyl metal bond. So this is a very interesting and for this catalytic cycle. So here we have seen that use of the solvent can make this, but as our methanol is not deuterated, so we will have this acid in most of the cases. Okay, so we will discuss the another important point. We will discuss another important point in this week. Another topic is the discussion. We have discussed the oxidation and reduction reaction but of the CO. But we have know that CO is highly stable molecule. So how we can activate this CO for the oxidation and reduction reaction? So to this is possible through the coordination of CO to a transition metal and then subsequent addition of a nucleophile to the carbon atom with the decrease of the CO bond order. So the activation of CO. So how to active this CO? So then the metal plus we are having a metal which will coordinate, that is the transition metal, coordinate to the CO, and now for this coordination 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 through this coordination it will become the metal and C, as this is coordinated from, so here some of the carbon electron density is donating to the metal. Now this bond order of this CO can decrease somehow by from 3. That's why this CO bond strength now will decrease. Now if we use any nucleophile, that is the nucleophilic activation, this nucleophile can attack to the carbon atom to generate the metal Nu. So this is, and then it's undergo the reductive elimination as the same catalytic cycle, and we can have the different carbonylated product. So this is the so the idea is even this nucleophile, that is any weak nucleophile like H2O, should perform this reaction. So for that we have the Haber-Bosch reaction with our catalyst H with the catalyst is H Fe CO4 minus. So this is our active catalyst for this carbonyl activation reaction. So how this catalysis is happening, we have not sure for the catalytic cycle, we have different mechanism for this catalysis. Now in one thing we have this H Fe CO4. Now this will undergo the carbonyl to give the FeCO5. This is our active catalyst plus H minus. Now this H minus can react to it H2O H minus react with H2O to give H2 plus OH minus. Now this OH minus is entering into this catalytic cycle to give entering in this catalytic cycle to give FeCO OH. So that is OH minus is attacking one of the carbonyl center of FeCO5 to give this thing. Now then it undergo the CO2 elimination step. This double bond will leave and this will leave. So and the hydrogen, this hydrogen will exchange to give this catalyst back, and then with the CO2. This is the one cycle for this. Another mechanism is we start with HFeCO4 minus, then we have perform the H2O is converting to OH minus, and then another H become H2FeCO4. Now this undergo the H2 elimination to give FeCO4. Now again the insertion of CO to give our catalyst FeCO5. Now as the thing happen in the same, this OH minus will again attack to one of the carbonyl group to have the CO4 FeC double bond O OH. Now they again undergo the CO2 elimination to generate the catalyst and to give CO2. This is the main catalytic cycle for this reaction, that is for activation of CO2. So this perform as the homogeneous catalyst medium for water gas shift reaction. So this is we have discussed the homogeneous catalyst CO2, homogeneous catalyst CO oxidation, that is the water gas shift reaction. So now we have our another kind of reaction, that is the mechanistic study of Fischer-Tropsch synthesis. We have discussed that is the Fischer FISCHER Fischer-Tropsch reaction mechanism. So that is in this mechanism, that is it is the reduction of CO to hydrocarbon. Different kind of. Now here we are using our catalyst surface. So here in this medium it is the heterogeneous catalyst. Here this is the heterogeneous catalyst. So heterogeneous catalyst medium, though the mechanistic of this is not clearly known, but a possible mechanistic diagram can be drawn based on the thing available. So first we have our metal plus CO, which undergo MCO MCO. Now in presence of H2 we have our hydrogen, then this M is basically becoming double bond OH, and that is the eta 1 formyl complex, eta 1 formyl complex. Then it undergoes the H2, which is M these types of eta 2 formaldehyde complex. Now these undergo in presence of again H2 to give M OCH3 in presence of H2. Then OCH3 can in presence of H2 can convert to methanol. Again this can give the metal, this gives the metal hydride complex. This can take part again the catalyst. Now this one also in presence of H2O can give MCH3 again, then it can give the MH, that's hydride, again CH3. Now it can eliminate the methane CH4. Again this MCH3 can take this CO to give COCH3, which in presence of hydrogen can undergo CH2 CH3. Now in presence of again CO, it can be CO CH2 CH3 and so on. So here this is the mechanism. So this mechanism in mainly the heterogeneous catalyst medium. So that's why the catalytic study or the mechanistic study for this thing is quite different. So this is the possible mechanism for forming different hydrocarbon in Fischer-Tropsch synthesis. Here, in this catalytic cycle, M represents an active site at the catalytic surface, that is the heterogeneous, or a free coordination site on a dissolved molecular complex, that is the homogeneous. Clearly, try to describe the process that occur at the catalytic surface comparing with the molecular example from homogeneous phase. However, this is a plausible, that is the expected mechanism, but this procedure is problematic. Why? Because here this each step is in practice, however, it may not be totally feasible, and this can generate a mixture of product. So the particular mechanism for this reaction, this is one of the possible mechanism which can be obtained. For the particular mechanism for this heterogeneous catalysis reaction is very difficult to obtain. So mainly this Fischer-Tropsch synthesis, so Fischer-Tropsch synthesis synthesis can be, so NCO plus 2 H2 to NH2 is can be converted catalytically a CH2N, that is the hydrocarbon, plus NH2O. Now here the delta H is 165 kilojoule per mole. So here you see that, so now, so this hydrocarbon can be the petrol, diesel oil, and waxes. So the synthesis, so the CO plus H2 produces this thing in presence of catalyst, but the this is the 50%, in this is 25%, and this is 25%. So the problem is specificity, that is we are not getting any product specifically in presence of the catalyst. That is a very big problem of, as also the reaction condition is harsh, so the catalyst mm, mm, is not so suitable. But in uh, South African country still uses this process to making the synthetic fuel for different thing. So this may maintain the synthetic fuel. So synthetic fuel, that is petrol, diesel, not from the natural oil. Also, the another catalyst which is known for this Fischer-Tropsch synthesis is the rhodium, CO 2 minus. Here, this catalyst in 300 bar pressure. This catalyst requires the harsh condition, that is the 300 bar pressure, also that 250 higher temperature. But this at lower temperature, this catalyst acting as an homogeneous catalyst and is become the soluble rhodium carbonyl formulation of zinc. So as without any selectivity, and the selectivity is less, but still we are using in this catalytic thing for preparation of synthetic fuel. So another thing, at the end of this session, one thing to mention for the water gas shift reaction, that with this continuation of Fischer-Tropsch, that another catalyst, that is the rhodium 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 I2 CO2 minus, like the other carbonyl, and rhodium 3, this is rhodium 1, I5 CO2 minus. These two rhodium complex also catalyzed for water gas shift reaction. So this is like water gas shift reaction in homogeneous system, and these things are soluble in the medium. So the importance of homogeneous system is required because these give the less harsh condition than the heterogeneous system, and it also gives some of the selectivity. So the water this reaction this rhodium, now this rhodium 3 species is transferred to rhodium 1 species. So now we need to see the reaction, that is the rhodium 3 species plus CO plus H2O is converted to rhodium 1 species plus CO2 plus 2H plus. Now this rhodium 1 species plus this 2H plus converted to rhodium 3 species plus H2. Now the overall reaction is CO plus H2O give rise CO2 plus H2O. So these also perform the water gas shift reaction. So don't write reaction, this is reaction. Perform the water gas shift reaction. So I think we have completed most of the topic which is important in this today's sorry, as the meeting link getting closed. So with this I think we have completed most of the important topics in this today's, that is this week 11 discussion, and I have discussed most of the important topic with their catalytic cycle and explain all the catalytic step and the importance of this reaction. This, and also we have seen another types of reaction which we are discussing since last 2-3 weeks, that's the homogeneous catalyst reaction. But today we have discussed some mechanism for the heterogeneous catalyst reaction also. But we have seen that for the heterogeneous catalysis reaction the selectivity is an issue. So the mechanism and the reaction condition we need to develop accordingly when the selectivity is an issue. Selectivity is low for this thing. So for the Fischer-Tropsch synthesis, the mechanism which we discussed, but now the thing is more developed, and we can modify the heterogeneous surface and to get our desired product. So so we have completed the 11. So with this we have completed the 11 week, that is the 11 discussion series session for the week for this course. Now the only one week is remaining for this course, that is more than 90% course content has been covered. So now I want to summarize again for this week content, that is in this week we have discussed the oxidation reduction reaction of the CO, and again we have discussed the carbonylation reaction of carbonylation reaction. So that is the increase of carbon in different hydrocarbons, mainly the methanol, in using the rhodium catalyst is the Monsanto acetic acid synthetic process. So first we have discussed the water gas shift reaction using our catalyst. The we have seen that metal carbonyl, that is the iron carbonyl complex, beautifully catalyzing this reaction under normal condition. Then we have seen also at the last of this discussion there is the rhodium catalyst, that is the rhodium 3 rhodium 1 system, which is also catalytic this reaction. And we have seen that the mechanism of this reaction in presence of water and the attack of the OH minus coming from the water and the hydrogen to the carbonyl to get this thing OH2O, and water and CO2, for that is the oxidation of CO, carbon monoxide, to CO2. Next, another counterpart, that is the counteractive, that is the oxidation reduction of CO, is the water gas shift reaction, and the reduction of this CO to hydrocarbon is the Fischer-Tropsch synthesis reaction. Also we have discussed the heterogeneous catalyst mechanism, and we have seen that how the synthetic fuel can be obtained for this Fischer-Tropsch synthesis method. And at the end we have the carbonylation reaction, for where we have seen that how we can increase the number of carbon atom in a system using the our rhodium catalyst. Here the catalytic cycle is quite similar as we saw in case of C-C coupling or C heteroatom coupling reaction, that is the oxidative addition, reductive elimination. Now one term, that is the insertion is coming, and we have understand that insertion of the CO to the metal alkyl bond is important for this reaction, and this step is the slowest step of this reaction, and this is also the rate determining step. And here we are using iodide to convert the methanol to methyl iodide, which is a better. So, and apart from the oxidative addition reaction of rhodium catalyst, also we have last seen that Arn Eastman anhydride process, where we are using the methanol and acetic acid to the methanol acid, form methanol acetic acid to form the methyl acetate, and this methyl acetate again convert to the, in presence of CO, again convert to the acetic anhydride, which is a very useful industrially useful industry useful chemical. So I hope this is the last second last in question answer session series for this course. I hope the this series will be helpful. Whoever will watch this series at the later on, and whoever will watch this series later on, and this will be helpful to solve your portal assignment and portal assignment problem, as well as for your exam problems, and find better understanding about this course. Now only 1 week left for this course. Next year we'll see the most important part, that is the hydrogenation reaction for using the Wilkinson catalyst. We will discuss it in the next Saturday. So whoever which watch this course, if you have any doubt, just give the your question in the discussion forum, and discussion forum question we are trying to answer as early as we are getting it. So this is for you. Will I believe that this session will helpful for all of the people who will watch this video. So I will ask you, if anyone watching this series, I will ask you to join in the live in this, so that and get your doubt cleared. So only 1 week left for this course, so I hope this course will be very beneficial for your understanding the organometallic field, and mainly the introduction to the catalyst and how an organometallic compound is important in the field of catalysis, in also in the chemical laboratory, for synthetic the different product, for synthetic the industrially important bulk amount of product. That is, we have seen that acetic acid synthetic process 10 to the power 6 ton per annum. Also the conversion of the toxic gas CO to CO2. So this is the main thing of behind this course, to get transferred the knowledge of the laboratory to industry, and how the things, the knowledge of laboratory thing is applying to the industry for their uh, purpose. With this, I believe that this will be helpful for whoever will watch this video later on, and whoever will watch this video later on. And if you have any question, please come on this session, that is the next Saturday, that is the last session for this course, and to get your doubts cleared. And uh, I will there will be then final exam also. I hope this session will be helpful for solving the assignment problem. As no participant was there, so continue this session from my side. So hope you will come in the live session, in live interactive session. So please, if you have any question, please post your question in the discussion forum with the uh, with proper, I will try we will try to give your proper explanation as early as we are getting the question. So this is all from my side in today's discussion session. So thank you, see you in the next Saturday 5 to 7. So please join in the live session in this session and get your doubt cleared. Okay, thank you.